quantum mechanics is all fun and games until someone loses an eye. This work was started really by a blog post by Scott Aronson when he talked about his continued fascination with why quantum mechanics depends upon complex numbers rather than real numbers. And I wrote to him afterward and I said, I've got this toy problem that I have some of my students working on, or I'm going to get a student to work on, and we'll send you the answer in about 2 weeks. And that was nearly 2 years ago. So I'm going to give you the state of the art of the problem as of today, but just first a little bit of introduction. Most of you guys probably know by now that Erwin Schrödinger wasn't too keen on the eye that he discovered in his equation. I pulled a page out of his first paper on coherent state for harmonic oscillator, and he writes down the general solution for the energy eigenstates, and then there's a footnote 5, and he says I means the square root of -1. On the right hand side, the real part is to be taken as usual. So he thought he could get rid of the I, and I think it was only in correspondence with Lorentz and maybe some month later, after his initial discovery of his equation, did he finally convince himself that he couldn't get rid of the I in the equation. And it might have even been Lorentz who convinced him, not Schrödinger himself. Niels Bohr, here was Bohr's attitude about the I. He writes down the Schrödinger equation and tells us H is a differential operator derived by replacing the P's by operators in the Hamiltonian function. And then he says this nice thing: the purely formal character of the suggestive resemblance between atomic mechanics and classical wave problems is perhaps most strikingly illustrated by the fact that this resemblance can only be brought out with the help of the conventional device of complex numbers, which alone permits to condense the abstractions of quantum mechanics in a form as simple as this equation. So in a certain sense, it looks like Bohr thought that the introduction of complex numbers was a convenience. It helped the equations look pretty, but that it wasn't genuinely necessary. As I would guess, a lot of the talks in this conference have focused on, in quite a number of quantum reconstruction projects, the incompatibility of real vector space quantum mechanics with local tomography is usually taken as a principle for discarding that particular GPT. And I really don't need to say much on this, I'm quite sure. But the key thing to note is that axiom comes from considering composite systems or decompositions of systems. It's not about single system quantum mechanics. Since my earliest days, back when I worked with Howard in 1993 and 94, I've always been fascinated with the idea of trying to do all of quantum mechanics with single systems and distill from single system quantum mechanics lessons about composite systems. So here's what I would like to do. I'd like to find a single system reason to prefer complex quantum mechanics to real quantum mechanics. And to that end, I'm going to tell you about some joint work I've done with my new PhD student. He just arrived in Boston a couple of days ago. Basically, he did 99% of the work that I'm going to tell you about today, and I did what most old PhD advisors do, and I sort of sat on my butt and rubbed my belly and listened to him. So let me go down this route. You notice that I say a cubist single system reason, and really, I mean, the mathematics will stand or fall regardless of which interpretation you adopt for quantum mechanics. But the motivation for looking at this particular question, I think, really comes from the cubist perspective. So first, I want to say a couple of words on probability, the notion of probability in cubism. For those of you who don't know, Cubism subscribes wholeheartedly to Bruno De Finetti's notion of probability. And here's the way this is a paraphrase of something that Dennis Lindley said. De Finetti's paradigm is egocentric. So probabilities are something that single people use in their heads from this point of view. It's a tale of a single person contemplating the world and not wanting to be stupid. De Finetti realized that to do this, his statements of uncertainties must satisfy the laws of probability. So from this perspective, you use probability theory not because it describes exactly how the world is without your presence, but rather you use probability theory because you are in the world and you're navigating in the world, you're immersed in the world, and you don't want to do things that are stupid from your point of view. So the paradigmatic way of defining probabilities is something called the Dutch book argument. De Finetti introduced this in the early 30s, and basically it gives a meaning to the notion of probability. So when you declare some number P sub E up here at in this gambling situation, what it means is that you will buy or sell a lottery ticket that's worth $1 or €1 if E for that amount of money. So this number is something about this person. It's this person's willing to sell a lottery ticket for anything, including epsilon above this amount, or buy a lottery ticket for anything below this amount, including this amount minus epsilon. So therefore, the meaning of this number is essentially the price that this person would be willing to buy or sell a lottery ticket for. So that's about money. What does that have to do with probability? Well, the wonderful thing, the genius of De Finetti, was he noticed that if you add just one rule to that scenario, namely the rule that a gambler never declares these prices such that it will lead to a sure loss, then from that you can prove that you get all of probability theory back. For instance, you get the additivity of probabilities, you get Bayes' rule from it. So really the structure of probabilities comes from this idea that you shouldn't be stupid. You should never declare prices that will lead to a sure loss just on one shot. I use this word normative. This is important in Cubism because it really emphasizes what the role of probability theory is now. So here's what I mean by the normative reading, say, of the additivity of probabilities. A gambler or an experimentalist in a laboratory, or anyone, may come to the conclusion for the ticket that they would buy or sell for the event E from one source. They may come to their prices for F from still another source, and their prices for E or F from another source. So maybe they read the Washington Post and come to this conclusion. They read the New York Times and come to that conclusion. And this is based on talking to their neighbor whose opinion they trust a lot. What De Finetti argues is that if these numbers, all gotten from separate sources, don't add up in the usual way, then a clever bookie can buy and sell tickets on E and F in such a way that the gambler will have a sure loss. Just no matter what happens, the gambler will lose money. So I give this as background because I want to say that Cubism views quantum theory as an addition to decision theory in exactly the same way that this is an addition to decision theory. It tells you what to do if you don't want to be stupid. So now we're getting to the motivation of this single system business. Particularly, we know that in quantum mechanics, we use the Bourne rule to calculate our probabilities. There's a probability on the left here, but there are no probabilities under usual readings on the right. This is a quantum state, and this is a measurement operator. These things, quantum states and measurement operators, look logically prior to the probability assignments that are calculated by the rule. What I'd like to learn is how to read this thing, how to read the Bourne rule in normative terms, similar to the way Diffinetti reads the rules of probability in normative terms. So now the question is, how do we do that? You can get some good guidance from a 1951 paper by Richard Feynman, where Feynman said, and by the way, the paper of Feynman's was titled "The Concept of Probability in Quantum Mechanics." So Feynman says, the new theory asserts that there are experiments for which the exact outcome is fundamentally unpredictable, and that in these cases, one has to be satisfied with computing probabilities of various outcomes. But far more fundamental was the discovery that in nature, the laws of combining probabilities were not those of the classical probability theory of Laplace. What has changed, and changed radically, is the method of calculating probabilities. And I like the way he's holding up his finger in this photo, because I do think he put his finger on the real issue of what's going on in quantum theory. It's that the rules for combining probabilities seem to have changed from the classical case. Now, of course, he was thinking about the double slit experiment, like he emphasized in his 1964 lectures, when he said, we choose to examine a phenomenon which has in it the heart of quantum mechanics. In reality, it contains only one mystery. So, you know, we all know the usual story. If we have a particle detector here and we don't have detectors at 1 and 2, then we see an interference pattern, or we see a probability distribution that looks like it's got interference. On the other hand, if we put detectors in front of the slits, then we see this different kind of, a simple bimodal pattern. From my point of view, or from Cubism's point of view, what he's doing is saying there are two experiments here. And for the two distinct experiments, there are different probability distributions for the outcomes. But what quantum mechanics provides through these amplitudes is a way of connecting the probabilities in one experiment to the probabilities in another experiment. Two experiments, in principle, the probability distributions might have nothing whatsoever to do with each other. But the role of quantum theory is to give some kind of glue between the two experiments that ties them back together. Now, I think that is the essential point, and I'll try to make that argument in a minute. But about Feynman's actual statement, I would say this: by introducing complex amplitudes, it distracts from the seminal point that it's the way probabilities combine that is the unusual feature. And besides, this is just one experiment. There's no sense which this single double slit experiment is indicative really of all of quantum mechanics. But this can be remedied by generalizing his considerations. And here's the way I'm going to do it. I'm going to focus all my attention on finite dimensional Hilbert spaces. And here's what I'm going to imagine for my scenario. There's a quantum system, and in the quantum mechanical formalism, we write down a quantum state for it. We send this system into a measuring device of one variety. It reemerges in a new quantum state, and then goes into a further measuring device. So the way to think about this is this measuring device at the end is like the screen in the double slit experiment. Whereas this measuring device in the intermediate space is like putting detectors at the slits. So if this measuring device were turned on, it would be like measuring whether the particle went through the upper slit or the lower slit If it's turned off, then this is like just seeing the interference pattern on the screen. So there's a quantum state, there is a quantum measurement here, a new quantum state emerges, and then there's a second quantum measurement. Now, to generalize Feynman, we need to be careful how we choose these things. And the way I'm going to specify this is, this intermediate measurement is some fixed or fiducial minimal informationally complete reference measurement. So that means that the measurement operators have to span the full space of operators. On the other hand, the measurement over here is not just a single measurement like in the double slit experiment. Over here, I'm considering any quantum measurement whatsoever. So we have a single fixed measurement, reference measurement. This is like introducing a coordinate system in relativity. And then we've got just any measurement whatsoever over here. Now, notice that there is an on and an off switch here. Suppose that the on switch is on, just like you see it here. But conceptually, I take an eraser and I erase the quantum state. And I erase the measurement operators. So I've got a device here, but I'm not using the quantum mechanical formalism anymore. There's some device, and it has a registration, some value R. And now let me erase these measurement operators as well. The only thing I'm leaving behind is this probability assignment for the outcomes, these conditional probability assignments for the outcomes, and this total probability assignment. So here's what we've got. I've erased the quantum state. I've erased this quantum state. I've taken away the information that this is a quantum measurement. All that I'm leaving behind are the various probabilities for the clicks in the detectors. Is there a relation between those probabilities? Well, there had better be a relation in any gambler's mind, because if the probabilities don't satisfy the law of total probability, the gambler is being stupid and can be led to a sure loss in an appropriate betting situation. So the point here is that the law of total probability has nothing whatsoever in this scenario, has nothing whatsoever to do with whether we're talking about classical physics or whether we're talking about quantum physics. It's just the way that the probabilities must fit together to avoid sure loss. I'm going to adopt, for further talking, a kind of vector notation. So this is like looking at the component of a vector. I'll call the vector P of E, and this is the jth component of P of E. And so what I've got is a matrix relation. So this is a stochastic matrix times a probability distribution, or a stochastic matrix times this vector leads to a new vector. In personalist Bayesianism, the law of total probability is normative guidance. It doesn't tell an agent which probabilities to use. It only says how they should fit together. Now, suppose we take the switch and turn it off so that that measuring device is not doing anything anymore. That's why I've fuzzed it out. Well, now we've got the quantum system going through it, going directly through it without any change, and then we've got a quantum measurement at the far end. If we're going to read the Bourne rule in normative terms, then we say, this way of calculating probabilities is there to guard us against doing something stupid. But what I'd like to know is, can we do better? Can we make it clearer that this too is normative guidance in the sense of Dutch book, or along the lines of Dutch book, but conditioned on some objective feature of the world that we're immersed in? So this is just another way of thinking about GPTs, and maybe it's pretty common to how Howard and Marcus, and I don't know who else I see in the audience. But this is the way I want to think about the GPTs particularly. All right, can we do better? Well, yeah, we can. Through a simple manipulation, we can cast the content of the Bourne rule, this thing that we saw here, in these terms. So we have the probability for when the intermediate device is not in place, written in terms of the probabilities that we used previously in the law of total probability. But there's an extra matrix in here that depends upon the details of the reference measurement. It depends upon the outcomes of the reference measurement and the quantum states that are subsequently sent from the reference measurement. If you look at this equation and you compare it to what we saw in the law of total probability, the sole difference between the two is that in the quantum case, this matrix phi, this thing that I'm calling the Bourne matrix, is not equal to the identity. So from this point of view, what we mean by classical physics is the extra assumption that Q just equals this with the identity in place here. And what we mean by quantum physics is that phi is not allowed to be the identity in this relation. So there's the law of total probability, which is a logical requirement. It's based on not wanting to be stupid. But the further identification of this with, say, the right-hand side where I put phi as the identity would be a physical statement. Not allowing phi to be the identity is a different physical statement. Namely, it's representative of our being in the quantum world. So we have the story of Feynman, the double slit, but now it's the d squared non-orthogonal slit experiment. In this form, I would say I'm sold on it. What's unique in the quantum case is that the laws of combining the probabilities from the one experiment to get the probabilities in the other experiment is not given by what we expect just from the law of total probability. Like the law of total probability, the Bourne rule is now written in pretty obvious normative terms. I'd like to think that Bruno De Ferretti might say, this is a good way of thinking about quantum theory. Okay, so this is the background of where we're going to start to make a distinction between complex vector space quantum mechanics and real vector space quantum mechanics. Here's some thoughts. The phi that went into that relation is variable. It's not universal. It depends upon what kind of measurement we've chosen as our reference measurement. This suggests that maybe we should look for the special cases of phi for telling us something more interesting about quantum mechanics. We know that phi can't equal the identity. That can be proven. But you might ask the question, well, how close can phi be to the identity? Or another way of saying it is, by adjusting the reference measurement just right, how close can we make the Bourne rule look like the law of total probability? We can't make it identical, but how close can we make it? Then I'm going to claim that when we find the phi that gets as close to the identity as possible, then in some sense, we have identified the irreducible quantumness of the Bourne rule. We've measured its minimal distance from the identity. It was a difficult paper to write, and unfortunately, I didn't reference it in these slides. But it's a paper by John DeBroda, Blake Stacey, and myself, where after a lot of toil, we finally proved the following result. If we define the irreducible quantumness by the distance between the identity and this phi matrix based on a norm, then we can say that whenever the famous SIC POVMs exist, then that's the measurement to use for the reference measurement. Namely, the output states and the measurement operators are just proportional to each other. All of them have the same weighting factor, some value alpha, And if we look at the Hilbert-Schmidt inner product between any two measurement operators, it's just equal to a constant. So this quantity actually is minimized, is always lower bounded by what one would get if one had a measurement of this structure. And it's achievable, that lower bound is achievable if and only if a set of operators with this structure exists. In that case, the Bourne rule becomes this little expression here, which is to some extent simple, or at least it's simple to those of us who've acquired a taste for it, like a good Irish stout. Where does it come from? Well, when you do the optimization problem, basically you find that you can achieve the lower bound when phi takes this very simple structure. This is the symmetric, informationally complete thing. But it might also notice this. We get a particularly pleasing expression for the Bourne rule when the E's form a von Neumann measurement. So previously, I allowed the second measurement here to be anything whatsoever. Suppose I now restrict myself to a von Neumann measurement. Well then, this expression simplifies still further. It becomes this, and lo and behold, there's the law of total probability buried in the middle of the Bourne rule. The key distinction is that it's got this weighting factor in the front of it, and it's got a overall -1 in the expression. That apparently is enough to change everything. So let's go back to this result. Irreducible quantumness is defined by this, that minimizes this norm distance, but I didn't mention what norm I'm using. And the reason I didn't mention what norm I'm using is because it works for any unitarily invariant norm. So for instance, it works for the trace norm or the Frobenius or Hilbert-Schmidt norm. It works for all of the Schott and P norms. It works for the Chi-Fan norms, and I don't know, whatever else you might find in Horn and Johnson's book about matrix algebra. It works for all norms, all unitarily invariant norms. Whether it works for other norms that aren't unitarily invariant, I don't know at this point, so I really can't say anything about that. So we get this pretty expression like this. If one of these seek measurements exists. Do they exist? Do they always exist? Well, this is a big open problem. No one knows. The current state of the problem as of March 29th, 2021, Marcus Grossel allowed me to use this slide of his. The state of technology at that time was that there is numerical evidence to many, many digits, sometimes to thousands of digits, that for every dimension up to 193, a SIC POVM exists, and he also did numerical work in some higher dimensions. But also he's invested loads of time into finding exact algebraic solutions, and one can find an exact algebraic solution all the way up to dimension 53, and then these sparser dimensions. In fact, I believe these 487, 787, and 579 are in green because it was still an ongoing computation at the time. But I believe that loophole has been closed, and these are genuine solutions. The message from their appearing to exist is that a lot of people think that it's just an open mathematical problem, and eventually someone very clever will prove that they do exist in all finite dimensions. I should mention that the group in Poland, in Gdansk, has a prize for 5 recalcitrant problems in quantum information. And one of their prizes is for if you can prove the existence of a SIC POVM in an infinite class of dimensions. So for instance, if you could prove it in all odd dimensions, or prove that they exist in all prime dimensions, or some such, then the prize comes with, I think, a 2,000 or maybe 2001 euro. You get some money if you can prove this. I would get satisfaction, but you could get some money. Okay, so this is the complex case. You can get a rather simple expression for the irreducible quantumness of the Bourne rule. What powered it? Well, what powered it is, in the complex case, we're aided by the happenstance that the maximal number of equal angular lines, the number of projectors for which we can get this constant overlap, for dimension D is equal to the dimensionality of the space of linear operators, namely D squared. So you can find D squared projection operators that all have the same Hilbert-Schmidt inner product with each other. But remember, this talk is supposed to be about what's wrong with real vector space quantum mechanics. And so from this point of view, one might ask, do we have the same happenstance in real vector space quantum mechanics? So here's a little chart. This, I believe, is the most that's known in the real case. So on the left-hand column is the dimensionality of the space. This is a real vector space. The dimensionality of the operators is the previous number times 1 and divided by 2. So we've got 2 times 3 divided by 2. Therefore, the dimensionality of the operators, of the Hermitian operators, is 3. So this is D times D plus 1 over 2. So 3, 6, 10, so forth. Grows like that. On the other hand, the maximum number of equal angular lines has been proven in these dimensions. In the first case, in dimension 2, the maximum number of equal angular lines is equal to the dimension of the operators. In dimension 3, it happens again. But in dimension 4, there's a divergence. You can't find so many operators, so many projection operators that are equal angular, so as to span the full space. They just span a subspace. That happens again in dimension 6. In dimension 7, interestingly, you get back the property that the maximum number of equal angular lines is equal to the dimension of the operator space. But then it apparently doesn't come back again, at least out to dimension 17. So what I'd like to know is, if we restrict ourselves to real vector space quantum mechanics, what plays the role of the seeks for our previous question? So what phi plays the role of minimizing this quantity when we have real vector space quantum mechanics? You can prove, just as you could before, that a hypothetical structure that looks simple like the phi seek, namely only depending upon 2 parameters, you can see that that provides a lower bound. But whereas in the complex case, you could always achieve the lower bound, in the real case, you won't be able to. So what's the answer? Well, I've got no clue, really. But let's see what happens in the first interesting case. The first interesting case is dimension 4, where the number of measurement operators we need is 10, but the number of equal angular lines, the maximum number, is only 6. So let me present a preliminary investigation. This is the special case where the output states from the measuring device are just proportional to the measurement operators. So this was satisfied by the seek measurement. These were the seek measurements, and then these were the seek states. In other words, we just used Luther's rule on the input quantum state. So we go back to this diagram. we go here, then what happens is this is a seek measurement, and the output state corresponds to the answer that was found from that measurement and goes over. So this is of that structure for our preliminary case. For a while, we thought that this gave the optimal solution to the problem, measurements of this structure. Only recently we discovered that actually the output states should not coincide with the measurement operators to get true optimality. So what I'm showing you is something that's close to optimal, but not exactly optimal. But here's what I promise you. This close to optimal is prettier than the exact optimal. The exact optimal we don't completely know yet, but it's even of more diverse structure. So what does the optimal phi look like? Well, it's this ugly thing. So this is a 10 by 10 matrix. And we were able to do enough numerical work that we could get a good guess at the structure. And we've confirmed the good guess at the structure. But we're left with one floating parameter, f. So this matrix depends upon a single parameter, f, in these various combinations for the terms. One thing to notice is, if you look at the diagonal, we get q, 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 and then u, 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 u. In the case of the seek measurement, all of those were identical. In this case, it's not. So what that tells you is that the weights on the optimal POVM are not identical. They come of two different weights, which is was an unusual feature to discover to begin with. But anyway, there's the general structure. Particularly, you'll notice that here we are in dimension 4. We've got one free floating parameter, and we've got this rather complicated looking structure in comparison to what it looked like in the complex vector space case. So it's just a bit different, I would say.
So time is almost up, Chris. We have a minute or two left.
And I have about 2 or 3 slides.
Great.
Fine. So there we are. What is the value of f that minimizes our quantity? Well, in the complex case, it was very nice. Everything worked for every unitarily invariant norm. It turns out that this f depends upon which unitarily invariant norm you're using. So for each of the Schotten P norms, there will be a different f that optimizes the quantity. So what are we to make of this? So the Bourne rule, what does it look like in real vector space quantum mechanics when we use the optimal intermediate measurement? Hold on to your hat. There it is. Truly insightful expression, you might say. I say sarcastically. So I just want to ask this question. You tell me, which foundational principle looks better? Here's the complex case, and here's what the Bourne rule looks like when it's in the irreducible quantum form. And this is a candidate that's pretty close to the real answer for what it looks like in the real case. If you're wanting to find a principle that singles out quantum theory generally, or as in the case with all physical theories, if you can start from some simple, elegant expression and then try to find the theory as a consequence of that elegant expression within it, then that gives you good guidance. And I think this equation does give us good guidance. This one, I would say, it's dead in the water, giving no guidance whatsoever. So the moral I draw from this is that for a cubist, when it comes to real vector space quantum mechanics, it's just too complex to be taken seriously. And that's it. Thank you. Haha, Howard, that was 39 minutes and 58 seconds.
Perfect. So, do we have any questions?
I saw Bill Wooters raise his hand. I like Bill Wooters' questions. They're nice.
So, Bill, can you speak up if you're... Oh, now you should be able to speak, Bill.
Maybe he doesn't have his microphone turned on.
Do you have your mic? Okay, go ahead with your question.
Okay.
Hey, Bill.
Yeah, thank you, Chris. That was an interesting talk. I should know this, but what is the SIC POVM story in quaternionic quantum mechanics?
I don't think anyone really knows much. They're known to exist in dimension 2 and dimension 3. And a fellow named Madad, I can't remember his last name, did extensive searches in dimension 4 and 5 and never found the analog of a SIC POVM in the quaternionic case. But that's not very conclusive evidence. In the real case, there's so much that's known, like in the little chart that I put up. The reason you can't satisfy the SIC POVM conditions in the real case is there's just not enough freedom to get a solution.
Right.
All over. You just have basically one constant that's floating around, and you shuffle minus signs to get a gram matrix, or attempt to get a gram matrix that's positive semi-definite, then you have a solution. In the quaternionic case, it looks like there's a lot more freedom, doesn't there? Like in the complex case. So one might think that sure you can do it, but I don't think anyone knows much more than I just told you, just the numerical searches.
Okay.
Maybe Huang Jin Zhu has also done a numerical search, but I don't know.
Okay, can I ask one more quick question?
Yeah.
Is it known in the real case whether there's a finite number of dimensions or an infinite number of dimensions where those two numbers agree? That is the number of SIC POVM elements and the n max and the dimension of your operator.
Yeah, so there's a necessary and sufficient condition for when it's possible that was proven in the early 70s. And dimension 2 satisfies that necessary. So it's a possibility in dimension 2. It's a possibility in dimension 3. It's a possibility in dimension 7. And then, in fact, not only is it a possibility, but then one can find the maximal number. But in the next dimension up is 23, where it's possible. So that theorem already excludes that it's possible for all of these dimensions. But in the next dimension up, 23, it was possible. And I think within the last 2 years, someone proved that, in fact, you cannot achieve it in that dimension. So there might still be an infinite number of dimensions where the condition's satisfied, but it's not always in those, the previous theorem of Lemons and Seidel.
Right, got it. Okay, it sounds like it's a hard problem.
Yeah.
Thanks.
Bill, actually, where you would be great is if you could tell us how to visualize this darn thing that we've found. I think I asked you that in email once, and you said, "Oh, I don't think you had much guidance." But it would be nice to somehow visualize what this set of vectors looks like.
I have no answer to that.
Any more questions? All right. I guess we'll go to another online question. So speak up if you have a question. Who is this?
Hello.
Okay.
Do you hear me?
Go ahead, yes.
I hear you.
Okay, this is me. Yeah, thank you, Professor Fuchs, for this nice presentation. When we move to the probability theory, we have the two issues, main issues. One of the first one is defining the domain of the physically accessible probability distributions, and the second one is, normally when we deal with the evolution of the probabilities, we came up with the transition matrices. We are moving one probability distribution to another one, and we are talking about the quantum systems. The quantumness of the system probably shows itself in the structure of these transition matrices, right? Normally, if we come to the probability distribution, we are just talking about the probabilities and the transition between the probabilities. In that case,
I'm not completely sure what you're saying, but I want to say this.
When we are in the probability,
all of the structure of whether we're talking about this or that GPT in this language is transferred into the properties of these phi matrices. So you can write any GPT in this form, and what characterizes the GPT are the characteristics of the class of phi's that one can use. And you can characterize that easily in the case of complex quantum mechanics and in real quantum mechanics. And so it's a question of exploring what class of matrices are allowed in this expression for this or that theory. So I don't know if you want to call that a transition probability. It's the inverse of a stochastic matrix, but yeah, I don't know how that connects to your question because I didn't really understand your question.
Maybe my question is meaningless, but my question is this: when we try to define the evolution of the systems, in the language of the probabilities, we are going from the one probability distributions to another one, right?
Oh, I see. So you're talking about something like time evolution.
Yes,
okay.
Or any evolution. I don't know the interaction or anything. We're going from one probability distribution to another one. In that case, if I'm wrong, you can warn me. We try to express this transition by the transition matrices, right?
Okay.
Okay, and I say, if the system is a quantum system, if it has some quantum nature which cannot be reduced to the classical notion, then probably this quantumness of the evolution, or let's say the interaction, show itself in the nature, or let's say the structure of the transition matrix. And then my question is there a way to quantify the quantumness of the interaction, or let's say the evolution of the system?
So do you have a quick answer, Chris?
Yeah, the quick answer is if I considered a little modification of this scenario, then I can write down unitary time evolution, for instance, in exactly this same expression. So this would represent the initial quantum state, and this over here would represent the final quantum state. And there would be some transition probabilities between these two things, but this phi, this ineliminable phi, would still be there. So you can think of time evolution purely in terms of initial probabilities going to final probabilities, but it's not simply stochastic evolution because of the existence of this phi there. I think that's my shortest answer, Howard.
Okay, we have one more online question from Gilles Brassard, and maybe we'll wrap up with that. So Gilles, go ahead.
Thank you. Hi, Chris. Very nice talk.
Hello.
Even 1% of this is pretty good. Now, could you please put back the it's not pretty slide?
You mean this one?
That's it. That's it. Right. So you said in particular, one thing that distinguishes complex from real quantum mechanics is that in the complex case, the diagonal is constant.
Yeah.
Now, when I look at these horrible formulas, I don't see any reason to believe that Q is different from U.
Oh, maybe yeah, very good.
Maybe for some x, it would be equal. So what is it?
Yeah, so there is one value of f for which they are equal.
Right.
But then you ask, what norm does that minimize? When you choose that F,
Uh-huh.
and it turns out to not minimize any of the norms.
Well, you can invent one, the Windward number. That it would minimize, perhaps?
Well, it doesn't, let me go back. Where was it? Here. It doesn't minimize any from this class, the so-called shot and key norm. So you can get an unbiased measurement. That's one where you would have the same numbers all along the diagonal,
Right.
but it doesn't appear to be optimal for any of the norms. So it's an interesting measurement, and it's actually the one that we've become closest to visualizing. We've got a little way of visualizing it in some slides I didn't show in this talk, but it just doesn't appear to be optimal for anything.
Fair enough. Thank you.
Unless one changes the rules of the game. Thanks, Jill.
Well, thanks very much, Chris, and let's all thank Chris. And